Okay, without getting into enormous amounts of detail right now, but I will later, what you have here is the dark particle and the bright particle. This particle here is electricity. That's what electricity is. These two tied together are what an electron is, the two of them together. This is an electron, that's an electron. This is heat. When that moves into something, it makes something gain weight. And I know this for a fact, as I probably explained, or I have explained, about the weights and measures I work with. And heat changes the weight of something. The hotter it gets, the heavier it gets. Everybody thinks as it comes up. No. The hotter it gets, the heavier, because they've got more black particles. But electricity, when you flood something with electricity, it just changes nothing. No weights whatsoever. You flood your car with electricity, it does not gain even an ounce. You fill your whole car up from empty all the way up to full. There's just no change. Then you drive it and it's just empty, no change. It weighs the same amount. This has no weight. This has all the weight. We separated all the weight away from all the energy, and all that energy is all you want to put in your car. We should be able to get free energy. Now I'm going to get a little detailed, but it won't be too bad. Stick with me. Okay, my friends, this is going to be a lot of fun. This is going to be very interesting. I have some input on sterile neutrinos. Let me show you what we discovered. There's two types of neutrinos, and we, I believe, separated them. That means they're sterile. Normally they're together in a union. And if you can separate them, that means they're sterile neutrinos. I think we did this. I'd like to show it. Okay, what I'm going to do is focus in here a little bit. And you see the two little blue cones up there. You see what it says? Muon Neutrino and Electron. Oops. Hold on. Okay, like I say, I think I might have something to add here. Now, if you can see these particles right here, a muon neutrino and electron neutrino, though they were attached together, just like this, muon neutrino and electron neutrino, black and white. Two of them back to back make a photon. Now, so they're always attached together, the black and the white. You virtually can't separate them, except when you do Cherenkov radiation, which is what they do with the particle colliders, big ones. So what they end up having is a sterile muon, which is that black ball, and the electron showers come out, which is the white shower, just a spray of white. And they normally do this with Cherenkov radiation, which is decaying protons. Well, we use light. All right, so let's see what they claim and what I claim. This is from Fermilab, who we're going to be showing in a second. And this is from Don Lincoln's work here, same guy. And he's found the same particles that we found. All right, and we found them in a similar time frame, back around 2014. So we have one black one and one bright one. And they attach together as a unit, only they see them in a spray of basically debris, because they're not doing what we did, which is to get down to photon size. When they see their stuff, they're hitting huge things like this together, and they just get a spray of particles, and then they dig through. And they found these are the two smallest particles that exist. They keep seeing those over and over as the smallest ones that they can possibly find. And I agree, they are. And they didn't realize, though, that they came together in little packages called photons or electrons. An electron that we always thought was just a glowy little Bernie particle electron. No, it's attached to the black. They're just, these two are attached together. As you can see here, 2 and 2. They're biomagnets. And when we put them through the Venturi, and it was tuned correctly, the black cannot get through, only the white. So we created a sterile muon array here. All the black ones that are floating all around here, they can't get through. And the white ones are the electron showers. So we have separated these. That means we created sterile neutrinos. Now let's see what Don Lincoln has to say. And again, these are his particles from his article here, and they do exactly what he says. He says that the black one never changes size. It has a little glowy edge around it. And this one has virtually no weight whatsoever, but it has a big field. And that's precisely what I'm showing here. You see it? That's his, and here's is ours. There's no difference. Exactly identical. The glowy little stuff around the black, yes, that's exactly what he says. And the point particle, which is this one, to get very small, very big, and it depends on how fast the particle is spinning, how much glow there is, and what color it is actually. Because what we did was we made that field, a big field surrounds the tiny little particle. So let's say the particle is this big, that big, whoops, and it's moving down here, but it's got a big field around it. So everybody else has a field around their particles. So they push, and these shove back, and they just get out of the way. I'll show this a little more carefully shortly. But at this point, the particle itself, which it always says particle-wave duality. Yes, it does both, because the particle has a big field surrounding it. So the field has to push everybody else's field. So that creates a wave. And here is the particle. Now, we pulled the particle right out of the wave. And here, it couldn't get through with the black. The black just was too big, couldn't get through. So the black had to stay out here, and the white could squirt down to just little tiny slips of nothing. You see it coming through here? There's not one single taste, of black in here, none, zero. However, we did also have it where the black and the white could get through, and you can see the black pushing the white. Here, it's just desperately wants to be reattached to the white. So there has to be extra black ones floating around just in the space we're in, because they're attaching to these whites here. The white will not stay on its own for more than a bazillionth of a microsecond, and they reattach here. Now, I've suspected that if we could possibly intervene right here and just take the white, because the white has no weight whatsoever, and that is what you put in your car to make it run. So if you can just get it here before it bounces back into the black, we're golden. And this is the most simple design you could possibly have to harvest strictly the white, which is the electron showers. And that's what you need. Those are the things that are powerful. So I have, the new theory is dipole electron flood theory. And these are dipole electrons. They always thought an electron was just one little glowy spot like that. But it's not. They all attach together. Now, the only way you can separate them is to do what we did, put them through a Venturi like this, and then they separate. They just break apart, which we didn't have to do anything at all. Nothing like what they're doing at CERN and Fermilab and so forth. We just put it through the Venturi and it separates. And we can do this all day long, and we're only working with light, so we're not working with these big heavy-duty particles. But what happens, why is nuclear power so dangerous? Why is everybody so scared of radiation? Well, there's a good reason. Because when you break this particle, now you got a problem, because these are huge chunks, huge things go flying through the air, and if they hit your cells, your DNA, whatever, they cause all kind of havoc, destruction. And that's also, you can't use CMOS, just standard CMOS, with proton collisions. It's too big of particles. They smash the CMOS, destroy it. So, and that's what would happen when I went to University of Geneva for particle physics. I told them, I said, we're seeing these particles with CMOS, and they said, no, you can't do that. And I said, well, we're doing it. And they said, well, it's impossible. You can't do that because the CMOS would be destroyed, and because of the high radiation. And I said, well, we're using light. So we started with this. Right, we started with that particle. They start with this. So when they hit their CMOS, the only thing we can hit the CMOS with, the biggest thing is that they can hit it with things like this. And of course, yes, you're going to damage the hell out of it. It's like hitting it with a Mack truck. So they did actually reconfigure the CMOS and hardened it so that they could see. Because let me show you something. Don Lincoln was saying that when you observe, you change the particle, and that's just not right. That's called the observer effect, and it's just not correct, and I'll explain why it isn't right. And the only reason it isn't right is because they're injecting energy. It's called charge coupled devices. They couple into the charge somehow, one way or the other, how they do it, whether they put something in there or they inject light into it or whatever. We're just sitting off here to accept the particle that's been shed off of here. They're going into it to examine the field, and when they do that by shedding light into it, that's only more energy. Or if they have something in there that absorbs energy, well, yes, and that's how they say that's the observer effect, because that's the only way you can see it. We see it with CMOS. CMOS is just nothing more than taking a picture of it. It's your cell phone. This is done by a cell phone. I'm serious. This is done by a cell phone. All right, so don't forget, Fermilab's particles, this is ours. And we did this with green and blue and red and all of them. And it's the exact same particle, no difference whatsoever, just the color. And the color relates to the intensity. Hold on one second. Okay, this is the Fermilab article where I show the same particles. And this is from Don Lincoln's statements here. He's saying that, well, let me home in so you can actually see it. I think you should be able to. Okay, so we saw the two particles. Now, when they want to observe them, he says, if you magnify an extended particle, which is one of these, it will look bigger. It's because it's a bowling ball. You magnify it, it looks bigger. No problem whatsoever. However, a point-like particle, which is this one, will not change its size. But the more closely you look at it, the stronger the field surrounding it becomes. It just is absorbing more energy because you're sending energy into it to look at it. We're waiting out here for it to spit out its energy because we're using it as an interaction. Okay, so Don Lincoln's last statements here about this, it says, in summary, the extended particle, which is the black one, is a fixed size, does not change ever. Although they may have a fuzzy edge around them, that's that red glowy edge, or if it's green, it's a green edge, it doesn't matter. The point-like particles are mathematical abstractions with zero size. Basically, I have to agree with that. Well, I don't know about the size, but they don't seem to have any weight whatsoever. And when I show you the atomic bomb blast, that pretty much proves it. But even zero-size particles have an extended effect. Yes, they do. They're the ones that have all the effect. Due to the effect of the field surrounding them. Absolutely, I agree, Don Lincoln. I agree with that. Okay, Don is going to be going over the history at Fermilab, so I'm going to go over my history. In 1968, right during the Tet Offensive, I joined the Army, and I was in nuclear Nike nuclear missiles. Now, as I got out of the Army, I went deep, deep, deep. And I'm just going to play this, and I'll speak as I'm doing. This is stuff that I did right after I got out of the Army. And I went through everything, because this is at, like I say, 1968. So in early 1970, I was doing all this stuff, the same as they were doing everywhere else at the major places where they're doing big research. So I had all that stuff done, and for years, and because, see, the transfer right there, transfers energy is from light to atomic vapor. That's dipole flood theory, and there is right there, dipoles, that's all there is, two types of energy. There's polar and non-polar dipole particles. That's all there is. So what happened was I was destroyed for my opinion that there was no gigantic positive core and tiny little electron. It didn't work. So I'm just showing you that I have some credibility here. And I've been doing this my whole life. I've been in electronics and so forth. So, and I have right now, this is electron flood theory. We're going to go through this because I have some notes here in the back. I can sum this up very quickly. That's it right there. You can have almost all you need to know about physics right there. And I document everything I do, so as you can see. Okay, don't forget now, I have a whole new theory of nuclear physics. And at the very end here, this is all we need to know is this right here, basically. And this changes everything there is in physics. The muon neutrino, the mass, electron neutrino, the mass. You cannot control a sterile muon. It doesn't reflect, it doesn't absorb, it doesn't emit. How are you going to control that? The only thing you control is the electron neutrino, because that's the one that bounces. Anyway, we're going to get into this kind of deeply, but it's very simple. I mean, it really is simple. Now, so it's electron flood theory, and again, they are looking for these particles, which I think we found them. All right, these are the two particles. They sure look like it to me, only we use a light instead of the big protons, so we could see them very easily attached. Now, this is red. Red is a very weak particle. Now, the green here is much stronger, but it is identical particle. And we put them through the Venturi at the same time, and the interactions of them are totally, completely different. Now, you see these particles down here, the black, white, black? Then you got white, black, white. These are different neutrino flavors. And the same thing happens with the red. It happens to all of them. And then what happens is, as they stack up against themselves, they gain energy, because it fields compress, and as they compress, they just get energetic. It's just like they said at Fermilab. They're right, but they just don't have any mass. I'm going to show you atomic bomb going off, hitting a house, and how the first thing that happens, the house just smokes up. It doesn't even move. It just goes like this. Everything absorbs the electrons, which are just the white part, because then the black part comes afterwards. That's what a nuclear bomb does. It does fission first of all, which sends off the white, and then boom, the black comes up to try to fuse back to it, and as it comes, it just slams everything out of the way. That's what an atomic bomb does. We'll be seeing that, and I'll explain to you that we can do the same thing with light, but it's not quite on that catastrophic of a stage. All right, we'll come back to this again when I do the atomic bomb blast, because we'll see the Whistler wave, the white particles, no mass, and then the boom. All right, so now that we're going to be going through this stuff in some pretty good detail. Remember I said the green is much more powerful than the red? This is going through the same Venturi at the same time. The green just pushes the red out of the way and reconcusses way out here, much, much stronger. Same particle. As I showed you, the green, that's the green, identical same particle as the red, which is here. Same particle. And it does the same neutrinos too. You see the neutrinos? These are particles of light, but they just haven't got the energy that the one coming straight down the center that hits this Venturi has. The one that comes straight down the center is piling up on itself, and it's getting bigger and bigger and bigger, and then it's glowing exactly what a photon should look like. Normally it's not going to have this effect, I don't think, until it concusses, but it's concussing with itself. So we're seeing them out here. Normally I don't think you'd see these. I'm not sure, but I know they're concussing on themselves, and you don't see them until they build up enough energy and get brighter and brighter, as you can see coming down the line here. All right, here it comes down the line. The particles here, back here is another. You never see that. You're never ever going to see that. And once the energy starts to build up and build up and build up, because it's crushing all these particles out of the way, so it's gaining energy. This particle that's in here is gaining, and it's getting bigger and bigger and bigger, and then all of a sudden it fluffs into its photon phase from these neutrinos. They say the neutrinos change flavors. Well, yes, they get stronger and stronger and stronger, and poof, they pop into a photon. Now, the only time they see these photons is when they slam particles together. We're actually slamming particles together as they're trying to get through the Venturi. So we're doing the same thing, but we're doing it a little, it's kind of nice, actually. It works out really good. Now, this is the blue. The blue is just rocket ship fast. You see it spinning here? Well, we'll get into all this stuff. And these are all the particles that are in the air. They glow because this thing's trying to push them out of the way. All right? And then when they come through the Venturi out here, they come out and they create Higgs fields. That's another thing I don't think they have right. They have the Higgs fields decaying into the black and white. And I say no. The black and white, once it's opened up and separated, they come back together to form the Higgs. The Higgs is the recombination of the white back to the black. Okay, this is Fermilab. Let's see what they have to say about making these muons. All right, here it goes. This just came out 2 hours ago. And I did comment on here. Now, if someone would come up to this place and leave comments about Mudfossil University's research on the muons and electron neutrinos, I'd certainly appreciate it. So here we go. This is called How Fermilab Made the Particle Beam for Muon G2. Now, here's what they say.
In our experiment, the Fermilab accelerator division sends us a beam of protons, the same protons that compose our atoms. And the protons collide against the target, and they produce secondary particles which are called pions. The pions decay into muons.
All right, so they have to use huge particles. They smash them to bits, and then they continue on, and they continue to divide on down to these particles. Let's just go back so we don't miss a thing here. All right, so the first thing is going to be the protons collide against
The target. And they
okay, so there's a target. Well, what is the target made out of? The target is going to be something that they're going to try to throw off secondary particles. So it's not like these things split apart, although they do. But what they're trying to do is split off secondary particles from some substrate, which is the target.
Produce secondary particles which are called pions.
All right, so the pions are literally little bits and pieces of the target they're hitting. So the target pions, which is like, so that they're shooting down the protons. The pions are like this big, all right, because they just smashed something else, that's all. And now the pions keep coming down, and what do?
The pions decay into muons.
Okay, so now the pions, which are these things, decay into muons. Now, how they do that decay, I'm not exactly sure, but it's a pretty advanced situation. And then they go through all kinds of gyrations.
Are responsible for producing the muons that we need to form a muon beam, and we can inject it into our storage rings.
All right, I'm just leaving it. They just go through all kinds of gyrations. This is billions and billions and billions of dollars spent to do this, and I think we might be able to do it a little less expensively. Okay, I just want you to know, I showed before, I think, some of my work, but this stuff goes back to exactly 1970, and it's pretty good. This was advanced stuff. This was as top advanced as you could possibly get at the time. And this was my final conclusions, right here, that the transfer of energy is from light into atomic vapor. The photons, they're atomic vapor, and they have dipoles. It's all about dipoles. And it's two types of molecular forces. There's only dipole-dipole interactions, and there's polar and non-polar molecules. All right, I probably didn't have a lot of things right back then because I never had, but I knew they were dipoles. And my professor wanted he wanted to give me a B instead of an A, and I said no, I want an A. And he did give me the A because I challenged him to figure out the dipole molecular moment of some polar molecule, and he says I can't do that. I said I know. So he gave me the A. You see, I know that's bragging, but it's not bragging if it's true, and it's true. The problem is that these guys are focused on one little tiny thing, and there's always a big picture. There's always a big picture. And if you can't see outside of the little box you're in, nothing ever going to change for you. You're going to always be saying the same things. You have to take in new information and deal with it as it comes along. So let's see if we can get some new information and get this done right now. All right, now the reason I'm doing this and I'm so adamant about this is we really, really, really need to get some free energy. And I think we, you know, as I said, the only thing that charges up your car is white. Okay, that white stuff right there. That's electricity. It has no weight whatsoever, and it has all the energy. And if we can harvest it just before it comes back to the black, right here, put a solar collector basically right there and just run it right down into a storage. Look at the power this is creating. Absolutely, it's unbelievable. And this is because we have created sterile muons and electron showers. Just as they say, here it is right here. Muon neutrinos turn into a sterile muon. This means high voltage. See, muon neutrinos, high voltage electron neutrinos, and then they turn into just a sterile muon, a black ball, and electrons turn into these showers. All right, and this is called Cherenkov radiation. It's by a muon neutrino event. All right, and there it is right there. And this literally is fission, because we broke the black from the white. They're not supposed to be broken. That's fission. And that's what happens in an atomic bomb. And then fusion is when they come back together. So that's fission and fusion. And I'm telling you right now, that is black. That's dark matter. That is all the weight, and it sucks this white back to it with a vengeance. And that's what creates electricity. This is a very, 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 very strong sub-nuclear force. All right, it's inside the nucleus, all of these little particles. And I have some, we're starting to set up some really nicely looking stuff. My friend Oscar, I'll show you, Oscar did this. Very, very nice. I'll show you what our particles look like. But let's see what Don has to say about Fermilab. And they go back to the early 70s. Fermilab, I guess, does, yeah. And I was doing the same work they were doing, and I wanted to get into that, and they suppressed me. It just destroyed me, because I said we need to talk about dipoles. And they said, no, you're way off the mark. You can't accelerate light. They, oh, you're all wrong. And I said, well, see you later. That's what happened. What are you going to do? You know, this really is kind of humorous, because Don has already found the sterile neutrinos 10 years ago. Now watch. This is, it really is kind of humorous. Now here's what he's going to say. They've been looking for these things for 1,000,000 years. And again, this would have been done long ago if they let me into the field, but they wouldn't. They said, you have to say what we say, and you have to follow these laws, and you can't come out of this, and light can't do this, and da-da-da-da. Anyway, here goes.
Fermilab has long been known as one of the world's premier accelerator facilities studying neutrinos, with the first beams being built way back in the 1970s. Studies of neutrino oscillations began at Fermilab about 2 decades ago, and it is anticipated that they will continue for decades in the future. But the past is the past, and the future is the future. What neutrino mysteries are Fermilab's scientists studying now? That sounds like an excellent topic for today's video.
I agree, Don. Let's do it. Okay, Fermilab's search for the sterile neutrinos.
If you were to ask, where is the center of the universe? I'd have to tell you that this is a silly question. In a mind-blowing moment of physics zen, the answer is both that there is no center of the universe and that every place is the center. I made a video about that. However, if you were to ask, where is the center of the universe for the world's neutrino accelerator research program, a strong case could be made for claiming that it can be found at Fermilab.
Or it could be found at Rod Warren's garage, because that's where we found the muons.
The laboratory already has the highest energy and highest intensity neutrino beam facilities, delivering nearly a megawatt proton beam to make those neutrinos. In the future, upgrades to the accelerator complex will cross the megawatt threshold. The upgrade is called the PIP2 program, and all of this is in preparation for the Deep Underground Neutrino Experiment, or DUNE,
All right, and this is billions and billions and billions of our tax dollars, my friends. And if they're looking for sterile neutrinos, and I know they are, obviously, they just missed the boat, which is a little concerning, because I've been trying to push this on Fermilab since about 2014, so we're talking almost 10 years. And what I showed you is pretty hard to dismiss, that they are neutrinos.
Which will lead to crucial comparative studies of the behaviors of matter and antimatter neutrinos. I've made several videos about all of this, really, a whole bunch, and the links are, of course, in the description. But those facilities won't begin operation, and those questions won't be answered for years.
This is the problem, and it really kind of upsets me. I'm trying to be very reasonable today and nice, but this is they're really basically sort of walking around in circles, when if they're looking for the neutrinos, Don's already found them. Here they are. That's a sterile muon neutrino. That's a sterile electron neutrino. I showed it to you. There they are right there. And they create electron showers, and the muon is a sterile muon. So why are we spending these hundreds of billions of dollars since 1970? And they have not produced much. He says it's the center of the universe, but I don't know. I would like to see them look at my information. What I'm not showing is not nothing. I am not an idiot. I did all of this stuff. I understand this stuff very, very, very well now. And I will show you the electron flood theory model in a second. And let's see what Don has to say. Let me see what I can find that makes sense, and I'll clip in and out of what he has to say. How's that? Okay, I'm going to have Don give his explanation here, and then I'll try to give mine, and we'll see where we fall down on this. Here we go.
Internal. There's a lot of history here, most of which I'm going to skip over, but we know of 3 different forms of neutrinos that interact via the weak nuclear force. Those neutrinos are called the electron neutrino, the muon neutrino, and the tau neutrino.
Okay, let's discuss that. Now, I showed you the muon neutrino is that black ball. The electron neutrino is the white ball. And that's all that exists. The rest are just other particles that are hooked up back and forth with them. And they say the W and the Z boson, this is the white particle and this is the black particle. That's all that exists. And you took 2 of these together, it makes a gluon. You take 2 gluons together, it makes a photon. That's it. All this stuff is just little bits and pieces that are floating around. So they're calling them cousin particles, and they have a particle zoo. Now, and then they say the Higgs boson decays into these. These congeal into a Higgs boson. So they have it basically backwards. Here goes.
Each one is called that because they are usually produced with their cousin particle. Since the late 1950s, scientists have speculated that neutrinos might not be immutable, and they might be able to change their identity in a process of subatomic switcheroo called neutrino oscillation.
Exactly. That's, as I showed you, they get stronger and stronger as they come along, and then they finally get into the photon.
Between 1998 and 2001, a couple of measurements proved that this idea was true. Basically, neutrino oscillation means that what started out as an electron neutrino could turn into one of the other kinds, much as if a cat could change into a jaguar, then into a tiger, and, well, then back again.
That's exactly, he's talking about the phases as they concuss against themselves. They get stronger and stronger and stronger, and then they turn into a photon, basically. Those are called the flavors.
I've made videos on the topic, and as usual, the links are in the description. Researchers have worked out the probability that each type of neutrino can convert into the others. Most of the experiments told a more or less coherent story, but not all of them. There have been several experiments that measured more neutrino transformation than expected. This has led some to speculate that there exists at least one undiscovered type of neutrino that is involved in neutrino oscillation.
That's just not correct. These neutrinos change in energy. I mean, so they end up becoming the muon neutrino and electron neutrino when they completely separate. But the electron neutrino's energy value is dependent upon concussion. When it's just sitting around, just laying around doing nothing, it's what's called the cosmic microwave background. It's just a particle laying out there. And when other particles bang into it, it glows a little bit. That's what gives you the background glow of the universe, is the cosmic microwave background, is light particles that have slowed down to a point where they're just not moving anymore. Light doesn't travel the same speed. I think I've shown that pretty well too. Okay, so I say we can accelerate light, and that's a pretty obvious acceleration of the particle, which is right here. And then it becomes a photon. So here it's in the neutrino phases as it's gaining energy. As Don said, it can change to a different type of animal, which is basically just getting bigger and bigger until it just shows itself as a photon. And at that point, it divides, and we actually get fission. And when they come back together, that's fusion. Now, in a solar panel, all you're doing is letting light hit it and force electrons into whiteness. And then it's collected by a little receiver. Now let me show you what my hope is that we could do with this. All we use for electricity is that white. That's all we use. That's it. When you have to rip that white away from the black, that's hard to do. That's why when you generate electricity, you use a big motor and you force fields against fields and push those whites down into a battery, and then they're stored there. And when you push them down in the battery doesn't gain any weight, nothing whatsoever. You're just pushing the electrons in there. Now, we're using tiny little lasers. This was a construction laser. Just a simple construction laser, pulsed. And then a Venturi here. Very simple. And then this was the outcome with a cell phone. And the cell phone sits back here absorbing radiation. We're not pushing into it, which, as Don Lincoln would say, you change it the stronger you look at it. No, we're just looking at it from out here, so it comes out here. So we're not interacting with it whatsoever. There's no observer effect. Now, if we could do this, these little devices are so small. The laser that's inside this is the size of a pinhead. What's coming out of here is just raw juice. You could have literally 1,000 of these or more inside of a little shoebox. So this is a Geiger counter, but it's I'm just a mock-up to show what it would look like. But you could have any kind of outlet you'd want: AC, DC, any voltage, any cycles, USB, whatever you want. Or carry it around. There's no interface to any big power grid, nothing, and you can't get hurt with this. You're working with light. That's all. And all you do is take a little taste of this and run back to run your lasers. If they're right, and I'm just saying they, as the physicists, they claim that you should, a minimum, is get 200 times what it takes to run that laser, if you can do this, and separate the black from the white. That's my take on it. I could be wrong, and it could be much, much, much more than that. So if we, this is all you need to run a car. That right there. Now, how many of them you need, I don't know. But we can regulate the pulses, how many times it pulses. We can regulate the intensity of the laser. I have some new designs for the enclosure that the laser would go into, that we could absorb all this radiation and then just pump it right down, just like a solar panel. It's just as simple as that. Really, it's as simple as that. When you just get hit by sunlight, you're just bouncing one here, bouncing one there, bouncing one here. So you're collecting some particles, yes. But this is 100%. 100%. 100% you can get. Now, you can also get less than that. Okay, so this is 100% right here. All right. No black here, none, zero, zero. But the explosiveness of this and luminosity is energy. Okay, here is the difference between CERN and Fermilab and Lawrence Livermore and all of them and us. Rod and I worked strictly with light. Everything you see here is particles of light that were crushed and separated, basically creating these electron showers. And they work with these kind of particles. All right, we work with the tiniest particles there are. They work with huge protons and neutrons, and bam, they come together and they just create debris. So in other words, we work with this size, these little bits and pieces. But there's only two pieces, it's the black and the white, that's it. And sometimes they come looking like a photon from them. Sometimes they see the black ones, they see the green ones, they see the red ones. And I will show you in a second our representation. Now, so we're only working with these here. So we never see all the trash, basically, because X particle means a chunk like this. That hits you, that's going to hurt you. Some of these other ones can hurt you too. Some of them are just bits and pieces and scraps and half a dozen and 6 and 12. They call it a particle zoo, which it is. Because it's not just one thing that can explode and make a whole batch of different things, and every one of these is a separate different thing. They're all made of dipole electrons. Two dipole electrons together makes a photon. One dipole electron is what we would always think was an electron. And the black part is the dark matter, and it's also gravity. It sucks the white to it. The Earth has to be filled up with a lot more dark matter than white because it sucks electricity down to it. Lightning, bzzz, static, right to ground. Ground sucks electricity. Okay, so don't forget, if this works, this is raw electron showers. Raw electron showers. Using the simplest solid state devices. Very, very simple. Now, again, Rod Warren is the one that did this work. And in order to proceed with this, he's going to have to be involved. And somebody's going to have to support him and take care of him for all this effort he's put in, for all this time. My stuff is just the theory part. And we need some engineers and so forth. But Rod is the guy that knows the specifics on this. Now, my stuff is the theory, and this should give us free electricity right there. And let me show you what the story is with electron showers. All right, don't forget what they're going to use. This proton smashing and creating all these hadrons and all these anti-neutrino flavors and some electrons and muons. This is what they want to get down, is the neutrinos. Because the neutrinos can give you a few hundred billion electron volts to a few trillion electron volts. If you can do this, which we did, we created the neutrinos, sterile neutrinos. So I don't see any reason that we can't harvest that excessive amount of energy in something like this. Just squirt it right onto a receiver. And it's not even going to be out in the woods or out in the fields or anything like that. It's just going to be a tiny little thing in this box. That's so tiny, it's microscopic. Now, the thing with this device is you're not going to have a whole lot of battery life here. Batteries, I can't do much with the batteries. That's the way they work. They're doing a pretty good job with the batteries. But this just sprays battery juice continuously. That's nothing more than what a battery would put out. All right? The battery is here, and you put your device into it, and it goes right through it and sucks it back into the ground. And they know how to make these regulator circuits and everything else, so it's not a problem whatsoever. Very, very simple device. It's virtually just like a solar panel. And it goes into a collection, you know, regulator and so forth, and AC, DC, whatever you want. No grid, no pollution, no gases, no expansion, raw electricity. And it doesn't gain any weight. That's what happens. Well, let me show you that atomic bomb blast. I think I promised I would, so I try to fulfill my promises. what we're going to see, I'll explain it as we go through. Here we go. Okay, my friends, this is electron flood theory. Now, my good friend Oscar Rosales did this, and this is the dipole electron flood theory. Enter at your own risk. These things are for you to see and for others as a test. What do you see? Well, let's see. All right. Dipole electron flood theory. All right. Dipoles just mean a positive and a negative, just like a bar magnet. Now, this is a theory. The anatomy of the proton is not what you think. Dipole electron flood theory is a new atomic model that changes the nucleus from a completely positive into a dipole made of tiny dipoles called Dirac neutrinos, which have a black side and a white side, instead of a large positive-only core. Protons and neutrons are made of dipoles. All right, it's 100% 50-50, I believe, in certain stable quantities that we now call atoms in various sizes. And that's your atomic chart here, your periodic table. And all it is zones of stability. And that's why all these isotopes they just came out with something yesterday. It was how important isotopes are. They never realized how important. Isotopes are just nothing more than extra electrons or not enough electrons attached to the core. We'll go over that. All protons are odd-numbered dipoles, approximately 1823, something like that, which gives them an atomic weight of approximately 0.000585 atomic mass units. That's because that's what a neutron. Well, I'm talking about neutrinos. Let me just continue on with about this. I'm going to confuse you, I'm sure. Every neutrino is one of these 1823 dipoles. All right, there's an electron neutrino and muon neutrino. Each one of those is one of these dipoles, and there's 1823 of them. Now, neutrons are even numbers, 1824. So why is that? Why is one even and one's odd? 1823 means to become stable, to have an even number, I need to get one or give one up. That's what a charged particle is. It's charged. If somebody comes along and says, I could take that charge, and I will hook up with you and we'll work together, they lock together. If another one comes up and he says, hey, I'm going to come in here and, with the opposite particle and push my way in and attach. It gets a little confusing, but all it is the charge can attract or repel. Let's go with that. The way the dipole nuclei are set up is there's a dark muon neutrino core. I believe this is it right here. This is going to be the black core. All over there are going to move together. They don't worry about being together. The black ones don't push, they don't shove, they don't do anything. When they're in light, they're the carrier of all of these particles, which are being pushed by something. Light has to get pushed or bounced. All right, these just go along for the ride, the black particles, as far as I can determine. So the dark muon neutrino core is surrounded by these different layers of electrons. And the closer to the core, the tighter they're held. If you see something blue going, you know that baby's really rocket shipping out of there because it was held so tightly. Green is a little less tight, and then the red sort of just floats around on the outside because it's so far away from the core that it doesn't have all the energy. That's why we can work with the red. The green is harder to work with, and a blue you just can't work with. It's too fast. All you can do is see it, and it's done. The other ones you can see them tumbling and doing all spinning and all kinds of stuff. So this is the anatomy of the proton. So what is the particles that make up the nucleus? Well, there's a white electron, basically, and a dark muon. Right? The white is the electron neutrino, and the dark is the muon neutrino. All right? This is the differences from the standard model. right? And it goes on and on. Anyway, this is dipole electron flood theory. This is from my friend Oscar Rosales, and we're going to be setting up a very detailed history and the future of all this stuff, because I could see, once you understand what you're dealing with, the particles and how they work and how you can squirt them and so forth, this has never been known before. And it's because you had to stay with Einstein. You can't accelerate light. Well, we know that's not right. That's just totally wrong. And we can see the particles now, and we're using CMOS, so this is not a big deal. This is this simplifies everything extremely, because we're not using these particle zoos. We're not just searching. Like Don Lincoln says, they're going to be searching for the next 10 years, and we've been working at this since 1970. Well, that to me is not impressive. The other thing was, oh, by the way, this is kind of funny. Well, this is funny on a whole batch of levels, because this is from 2013. He found a dark particle. He found the muons. That's a sterile muon, and he still doesn't realize it. I got a hold of him back then, and I said, Don, I found your particles, and it didn't go well. It didn't go well at all. And at the same time, this is, like I say, this is funny on several levels. I also saw something from the Russians, all right, which was this. All right. And I contacted Don about this too, as I was contacting the Russians about it. And I said, Don, these black particles can separate from the white. They're out in space. This is a vacuum chamber with charged particles in it. And they expected them to come and separate from each other like in a lattice network. So all the pushing ones would push away from each other, and you see all these glowing particles, one here and then one here and one here and one here, and like a checkerboard looking thing. Think of it that way. But it would be cubical. However, they see this. They freaked out. He said, during the experiment, we contacted the Earth guys who couldn't believe it either. The guy from Max Planck locked himself in his office for 3 weeks freaking out, because they had no idea. Now, these white particles can separate from the black. I never thought that was possible. But on Earth, it's not possible. They will not come apart, because they're being crushed to Earth by the dark particle of the Earth pulling them in. So, I still haven't been able to investigate this with the Russians or anybody, because nobody will really get involved. But I would like to see some more experiments on this. They did a nice job. The Russians do some pretty good research. And at any rate, it didn't work out. But I can see that all those white particles want to go into those black. They all get attracted to the black. And then these whites are keeping the other one from, in other words, I want to get in. You say, no, we got enough here. And at some point, this will fill up a complete layer, and then there'll be another layer out there, and then there'll be another layer. This was as it was bouncing out in space. This, I don't know if they left it, how long they left it, but I would assume that's what's going to happen. So you end up having, the core is black, and then you have one layer pretty dense, and then you'd have a little slip zone maybe, and then another kind of dense layer, and then another maybe slip zone, because they're pushing each other away. These guys don't want to be against other white guys. They say, you stay away from me, I'll stay away from you. That's what it is, push to shove. And then they establish a pattern. It's called an interference pattern. And I'll show you how it comes out. When we put it through the Venturi, look at this. And this shows two things. It shows two things very, very nicely. First of all, it shows that light spins. You see this? It's spinning. Let me put these down. It's spinning. See, it's one time. Sometimes it spins to that way, and sometimes it spins over and goes under this way. Now you see this right here? That's not an accident. This is screwing itself through there. That's a drill bit. Now, what happens on the? This is from the other side of the Venturi up against a wall. Most of them come through the center. A lot of them go out to the outside, a lot of them go to this side. You see how finely detailed these lines are? Here and over here. All right, they are glowing as the spinning particles are pushing each other apart, concussing with each other's fields as they interact with the Venturi. All right, just you can see them. You see how perfectly separated they are? They will not touch each other. They hate each other. That's not just an accident they showed up like that. They hate each other, so they stay, you stay your line, I stay in my line. They call them interference patterns. They always said it was a double slit, and that's why they had these perfectly aligned patterns. No, it's because they push each other away. This is a single slit, all right, not a double slit. All right, so I'm going to recap up here a little bit. We can accelerate light, no question whatsoever. We can see light slowing down, no question whatsoever. We see light is a particle, no question whatsoever. We see it in green, we see it in red, we see it in blue, all the same particle, just different levels of intensity. And you can see it here, how the red is just pushed away and the green reconcusses way out here because it's much stronger. Same Venturi, same time, green and red. Red just gets pushed out of the way. These are the Higgs fields we see in our experiments as it comes out of the Venturi this way. All right, these are the Higgs fields as the white particles reattach to the black. They just form these fields. It's not these Higgs fields decay to the white and the black. It's when the white reattaches to the black. That's when you get the Higgs. All right, and here's one coming in on steroids. That's the white coming straight through and boom. And I believe I can see these forming the outside of these fields. The outside is really where the particle is. For some reason, it forms an inside pattern. And I can't tell you exactly why. But I'm pretty sure of this, and because of an anomaly that I saw. You see these? I believe this is actually creating and flowing into this field and creating that field. Now, we did have one that went backwards, and that's this one here. This one came out backwards. And these all came spinning the correct way, and this one's spinning backwards, and I believe it's gathering its energy into itself. And I believe I saw this one concuss with another field. You see how, let me turn this off. Sometimes it lightens up a little bit better. Look real careful at that pattern right there. You see it coming out of there? That little strip underneath that white particle? Why is it doing that? All right, all the rest of them are spinning just like normal Higgs fields. All right, and this one's got that little tail to it. Now, there's another action I see over here, too, is this one is turning purple and flattening because there's two fields impinging upon it. I don't know if you can see that or not. You see the purple one? There's a field to the top here to the right and a field over there to the left. They're pushing that, and then they're squirting that one out ahead of it into a different color. They should all be red. All right, they all started out red. The only way you can change them into a different color is to increase their energy or decrease it. Now, that particle, I believe, is the particle I'll show you right now. Okay, I looked at this thing for on and off, not just continuously, but on and off for 5, 6 years, 7 years. And then I finally realized, I think, what I see. And the reason is, I believe that the particle rides in this outside ring, and it forces the field to go inward. That's all I can take away from it. Because I could see from the other ones, as I showed you, the particle comes up, hits there, and then they seem to spin. And the outside is where all the energy seems to be. Like, you see this one here? No. Here's what happened. This, I believe, is the particle. You see how it has some crazy looking thing here? But it's just a white particle. It's not interfering with anybody yet. But now it hits this guy. So these particle fields are going this way, spinning, which is the right-hand rule. It spins to the right. Supposedly that's the deal. Now this one I say is spinning backwards, so it's spinning to the left. If it was spinning to the right, it would just come along and bang into this one, and they both keep spinning to the right. Instead, when it hit this field, its particle, which is on the outside ring, just like this one, only this one's coming this way, and this outside ring is going that way. So what would happen? This particle would grab a hold of this particle and rip it right off the ring and twist it right off. Now that's another exotic particle as far as I'm concerned. So you got this exotic particle was a backward spinner. Now you got this one is now a forward backward spinner. If it started as a backward spinner, and I think this one turned into a forward spinner. That's all I can say. This took me years. I look at that. I would look at it almost every day, and I say, how the hell did this happen? And I do a lot of that because everything's confusing. But I think that's it. So understand again, one more time. This thing's spinning backwards. It's spins like this, spinning, and it spins and hits this disc. This thing is hidden here, and the only place the particle is here. You see the field's gone now. The field's just sort of evaporated, and this went off to this way because it got ripped off. That's my interpretation of that event. So that's some pretty exotic physics. Okay, I showed you this from Oscar, and a fabulous job he's doing. And there's only one other possibility to this, and that is to have a layered black and the blue really tight down, and then have black on top of that, and then the green tight to that, and then have black on top of that, and then the red always on the outside, because you're always getting a bounce back. That's why it's dark matter. It's always in the center. You're never going to see it. Is it deep in the center always? I'm not sure. Is there a layer between each one of these? I'm not sure. But we're going to go over my theory of dipole electron flood theory, which changes everything. It changes heat and cold and electricity. It changes everything there is. Everything there is about matter, basically. And a lot of it's understood. It's not understood. It's just seen, but it's not understood. That's the problem. They can see it, they just can't understand it. And that's what we got going on here. They're spending billions and billions and billions of our dollars. I mean, just when you see the stuff, look at this. This is deep underground neutrino experiment. We did this for a couple $100. And we got neutrinos, and we can harvest them directly into our receiver. Something right here. This should be as simple as this. And you could have literally 1,000 of these lasers in here, collecting I don't know how many bazillion watts of power. I don't see any reason you can't do this. I see no reason whatsoever. And if you do it right, it shouldn't create a whole lot of heat. You'd only turn them on to the point of what you needed. And you could have all kind of backup in there. You need some kind of battery to fire it up to start it up. But a small battery, you're working with little tiny lasers, a couple of volts. I mean, a couple of little cells. And again, just think how that would transform the world. So I'd like to see this looked at. It's been ignored now for quite a long time. And I've really been pushing it hard, but it's tough to fight City Hall once they got in charge of all this money. And I got a feeling that's what's going on at Fermilab. I can't believe they can not understand that I'm showing them their own particles. It's impossible for me to understand that they can dismiss their own particles that I am showing. So what is the motivation here? I think there's got to be something to do with funding and status and all that. Other than that, I should have some engagement here. I am fully, I'm showing the evidence. I'm not just talking out of my ears. And I am a taxpaying citizen. This is a government-funded agency. And I pay taxes. I am a veteran, an Army veteran of the Vietnam era. And I've been doing this since then. And at that point, I worked on Nike Hercules missile sites. So this is not something I'm unfamiliar with. And I think I showed you all my paperwork that I did. I only showed that to just give myself a little validation that I understand this stuff. And if you don't understand that I understand, well, I don't understand why you don't understand. Do you understand? Okay, I got a few interruptions here, and I just want to make sure you understand. I think I might have already gone over this, but I want you to fully understand what the deal is. I say the only particles that exist are the little white particle and the black particle. Call them the W and Z boson. The white one is they've got all the energy, the black one's just got all the mass. If you took those two to glue together, you have what they call a gluon. I agree, they glued together, they make a gluon. You take two gluons and you have a photon. That's it. All the rest is just different energies as they're building energy or losing energy or twisting this way or twisting that way. These are the only two particles that exist, and these are the smallest configurations that are stable-ish. This one is not stable, a gluon. It is an electron, basically. It wants to attach to something. It wants to move into something. It's not happy on its own. A photon is different. Two gluons together are two bar magnets, and it can bounce. That's why we see them bounce off of things. And that's the smallest particle that exists that's stable. Photons of light are stable. They fly through the air, they bang and bounce and all over places. Now, they're made, though, of two unstable gluons. And the gluons are made of these two particles. A double of these two. All right? And then, of course, when they come apart and they reform, they make the Higgs. All of that stuff doesn't exist. Well, it exists, but it's meaningless because it's just different energy levels. This is what you need to think about. All right, so keep that frame of mind, and let's listen to what Don has to say here.
Speculated that neutrinos might not be immutable, and they might be able to change their identity in a process of subatomic switcheroo called neutrino oscillation. Between 1998 and 2001, a couple of measurements proved that this idea was true. Basically, neutrino oscillation means that what started out as an electron neutrino could turn into one of the other kinds, much as if a cat could change into a jaguar, then into a tiger, and, well, then back again. I've made
All right, I did explain that in the neutrinos gaining energy, basically. That's what he's talking about.
Videos on the topic, and as usual, the links are in the description. Researchers have worked out the probability that each type of neutrino can convert into the others. Most of the experiments told a more or less coherent story, but not all of them. There have been several experiments that measured more neutrino transformation than expected. This has led some to speculate that there exists at least one undiscovered type of neutrino that is involved in neutrino oscillation. However, this fourth neutrino doesn't interact via the weak nuclear force. Because of this, we have a special name for this proposed fourth neutrino, and it's called a sterile neutrino.
All right, if he's talking, he's got to be talking about the black particle. The black particle is the sterile neutrino, because apparently he just thinks there's one neutrino. But that's I can't understand how he's thinking that, because all of the charts talk about the muon and the electron neutrino. Here's right there, muon electron neutrino. I don't know what he's thinking. These are not I didn't make this. They say there's a muon neutrino and electron neutrino. Well, I agree with that. Now he's talking about a sterile neutrino, and when they're separated, they are basically they're not combined, so you could call them sterile. The muon really goes sterile. It turns into that black ball and goes all, and then it wants to get back together. Let me go back and see what he's saying again. Let's look. Let's make sure we don't. I don't want to say something that he's not saying. Hold on. All right, he's got all kind of other videos on the topic of the neutrinos changing flavors. Well, let's see what he has to say here.
The topic, and as usual, the links are in the description. Researchers have worked out the probability that each type of neutrino can convert into the others. Most of the experiments told a more or less coherent story, but not all of them.
All right, let me stop right there. They don't change it. Well, you start with the muon and electron neutrino. That's it. They get stronger or weaker, and the electron neutrino gets pumped up. So yes, it gets all kind of. They can make all kinds of different views of it and call it all these different names, but they're all originate from the black and white particle, which is the dipole electrons. So he's saying that some of them measure it this way, so nothing's correct. Basically, he's saying nothing's correct. Okay.
There have been several experiments that measured more neutrino transformation than expected. This has led some to speculate that there exists at least one undiscovered type of neutrino that is involved in neutrino oscillation. However, this fourth neutrino doesn't interact via the weak nuclear force.
All right, this, when he says the weak nuclear force, well, the black muon is not really affected. Well, let him keep going here.
Because of this, we have a special name for this proposed fourth neutrino, and it's called a sterile neutrino. By the way, I said that there could be one type of sterile neutrino, but there actually could be more than one. It's just simpler for our purposes to talk about the situation as if there were 3 ordinary neutrinos and 1 sterile neutrino. If there are more sterile neutrinos, this doesn't change what I'll say in this video. One experiment that reported the possibility of sterile neutrinos was called the LS&D experiment, performed at the Los Alamos Laboratory in New Mexico. It collected data and
all I can see here is money just gushing everywhere, and this is in the late 90s. They've been doing this, and he's talking about 10 years before they can really figure out anything. Look at the money they're spending. It's just phenomenal. You know, and they're bragging about how we're digging some discovery beyond everything. Well, if they're looking for the smallest particle that exists, I would hope they would at least think of talking to me. The design of the Dune detector, we designed a detector, this is just nothing more than a continuous job of walking around in circles. I'm afraid that's just what's going on. Look at this. Look at this. This is your tax dollars at work. They're looking for a sterile neutrino. I just showed you them on steroids. Sterile steroids. All right, if you're really deep into nuclear physics, you understand there's something called a Whistler wave, and it precedes an atomic bomb concussion. So when they look at a bomb going off, they see this brilliant in there. That's this. It's a sub light. It's a sound. It makes a sound. It makes a little just like that. You hear those little ripples. Then the white particles sweep out, being pushed by the black. The white, the house was here, and it burns, and pow, and then the black hits it, and that's it. The white has no mass whatsoever. The house just vaporized. And that's the same stuff you put into your car. And that's the stuff that we can harvest right here by putting it right here. Look. All we got to do is I'm saying all we got to do, I don't know if we can do it or not, but we damn sure should try. And it's been refused by Fermilab. The people that I contacted, I said, I found your particles, and maybe we can do something and get free energy. And they told me I was a tinfoil hat guy, and they needed billions of dollars in funding. Now, they didn't actually say that, but I inferred that, and they would not get it if they fixed this problem that we're having with energy. And they will never fix any of these problems because nobody cares to fix a problem. They care about where the next dollar's coming from. And their jobs. I understand that. It's just self-preservation, but it's not going to help us. And we hired them to do this job. And these are government agencies. This is Fermilab. Told me I was a tinfoil hat guy. Don't ever contact them again. Don Lincoln. Maybe you should contact Don Lincoln. Somebody should do something. This is ridiculous. They're walking around in circles using our money as taxpayers, just squirting it all around, having a good time. Because they're all highly educated, and they don't have to listen to anybody else because they got it all figured out, and nothing has ever worked. All right, I believe I showed the picture of the black pushing the white, and the white has no mass whatsoever, but it has all the burn. So in this case, an atomic bomb goes off. The first thing to leave is all the white. The next thing is the black comes after it. But the white is pushed out first because the white coats the black. The black always goes to the center of these huge massive things, and then they slam them together and then they go out. And the white goes out first because it's being opposed by all its fields, and then the black just follows it. So what you're going to see is the house just vaporize, and then it's going to be knocked down. I'm running it very slow, so here it comes. This is atom central. All right, the first thing you're going to see is just everything's going to glow, and then you're going to see it all just smoke up. Watch. It doesn't go anywhere. It's not going anywhere. It's just smoking. The wires, the poles, everything. And then all of a sudden, when it's almost all burnt up, then the wave comes of the black particles. Boom, there it goes. All right, let's let Don finish up here. Here he goes.
Definitive measurements that will tell us whether sterile neutrinos exist or don't. Fermilab's current short baseline neutrino experimental program is the very foundation on which future neutrino research success depends. Okay, so neutrinos are pretty cool. They have fooled scientists time and time again, from how they showed in the 1950s that the weak force interacts differently with matter and antimatter, to how they surprised scientists in the 1960s when it became clear that there were different types of neutrinos. Then there were the hints from the 1970s through the 1990s that neutrinos can change their identity. Who knows what future surprises they hold?
Don, you're going to have to look at my stuff, my friend. I know we didn't get along, but, you know, we got an interaction. I have a history with Don. And all I'm trying to do is be polite and scientific. And I believe this is about as scientific as you can get. As far as light goes, there's no reason you have to start with protons. There's none whatsoever. They're trying to get to the smallest particles. We're starting with basically the smallest particles. They wanted to get down to here, to electron showers. All right, they had to get down to neutrinos. They started proton-proton collisions. They create hadrons and all kind of beam axes, and decay of the hadrons creates flux of antron, this and that. But this is where you want to be right here. Is the neutrinos, energy of neutrinos. That's big energy. And again, I think we could make it, put it in a little lunchbox. You know, everybody's been comparing this to the things they see in Egypt with those little handbags and the carvings on the walls. Maybe they were walking around with bags full of energy, and the little watches they have on could be, hello, it's Roger, over. All right, so that's it. I love you all. All I want to do is have this seen by somebody. I'm a taxpayer, I'm a veteran, I'm a senior citizen, and that's it. I just want to be heard. And if this could get us free energy, just think of the difference in the lifestyle. Absolutely phenomenal it would be. And this stuff is right off the shelf. So, all right, I love you all. Thank you. Bye.